Right, so we've looked at the basic interest rate stuff. Now we move on to the mortality stuff. So LX is the number of lives left at a certain point in time. TPX is the probability a life aged X survives for T years. And then the topics around here are all the mortality annuity assurance type functions. Okay, so let me move that stuff out of the way. That was a failed first attempt, and let's start with a couple of nice little definitions. So one of the most basic pieces of actuarial symbolism notation is TPX is the probability a life aged X survives for T years. Okay, probability life aged X survives T years. Okay, and LX is the number, and we'll think about this a bit more, number of lives that survive to age X. Okay, out of a hypothecated starting set. So let's go back and look at some more of the maths here. When we look at exposed to risk and censoring, Nelson Island, Kaplan-Meier, that sort of stuff, we will be looking at how we actually compile these tables of LX, because it's not a trivial matter. But for the time being, we assume it's basically an underlyingly correct table of the number of survivors of a given cohort. So an example of a table of LXs will be age 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and LX is then the number of survivors. So we hypothecate that there are 1,000 lives born on a given day in a town, for example, and then we hypothecate how many of those will survive if if we just run that cohort of 1,000 lives. So it might be that there are 950 left at the end of the first year. It might be that 920 after 2 years, 913 after 3, 907 after 4, 892 after 5, 871 after 6, 833 after 7, 720 after 8, 666 after 9, and 612 after 10. For argument's sake, they're just numbers at the moment. And then what we can then say here is, well, what does this mean in terms of our probabilities? Well, we can see fairly easily here that what we're saying is the probability that a life age 0 survives for 1 year is 95%. Okay, so probability life age 0 survives for 1 year is equal to 950, which is that number, divided by 1,000, which is that number. Okay, and the great advantage of this is if I did a table of TPX, I'd need a two-dimensional table with T's and X's. With this method, I've effectively reduced that two-dimensional table to one dimension, because any value of T and any value of X I can work out. So for example, if I want the probability that a 4-year-old survives for another 3 years, it's that. So probability of 4-year-old survives for another 3 years, and that is simply, I take the age in 3 years, 833, divide by the number now, 907. Okay, so hopefully you can now see the general formula here is TPX is equal to LX plus T divided by LX. And that is one of the most simple but very, very important formula. It's how we calculate the probabilities that people have survived a certain amount of time. And on a related note, the notation TQX is the probability that you have died in that period, or the life age X has died in that period, which is simply 1 minus TPX for obvious reasons, and a lot of actuarial math really is that easy. It's just thinking about it in simple terms like that. Okay. So now the question that you might be asking is, well, what about lives that aren't integer ages or integer amounts of time? And all we do is interpolate, but there are two ways of interpolating: geometric and arithmetic. So let's look at that. So let's say we want to do the probability that an 8-year-old survives for 1.5 years. Okay, well obviously that is going to be L 9.5 over L8. We know what L8 is. 720. Okay, but L 9.5 is a bit trickier. It's going to be somewhere between 666 and 612. In fact, let's not make it L. Let's not make it 1.5. Let's make it 1.3. Then it illustrates the numbers a bit better. Okay, so what's the probability a life age 8 survives for 1.3 years? Well, L 9.3 is somewhere between 612 and 666. Well, I can do it linearly. Okay, and that is assuming, you can think about this yourself, assuming a constant rate of death. So the number of deaths per unit time will be the same at the start of the interval 9 to 10 as at the end, which you think about it doesn't make a lot of sense, because at the end there are fewer lives left. So this is a counterintuitive way of doing it, but it's simple mathematically, because we're just taking L10, which is 612, and L9, and we're weighting the two. So 9.3 is closer, this is the easiest way to think about this, it's closer to L9 than L10. So we're going to get 0.7 lots of 9. Okay, you're going to get 0.7 lots of that, and 0.3 lots of that. So it's 0.3 times 612 plus 0.7 times 666. Okay, equals whatever that equals. And then the other way is the constant force of mortality. Now the force here is analogous to the force in the force of interest, because it's basically the parameter that goes e to the minus something times t. So if that is constant, if the lives are decaying at a constant exponential rate, then that is a constant force of mortality. And this time we still have L9 and L10, but we take the powers instead. So instead of 0.3 times 612, we have 612 is the power of 0.3, and multiply by 666 to the power of 0.7. Okay, and I'll calculate those so we can see what the differences are. On the constant rate of death, we're going to get 649.8, and on the constant force of mortality, we're getting 649.32. Okay, so it doesn't make a lot of difference. Okay, so in terms of my probability that an 8-year-old survives 1.3 years, it's either going to be 649.8 over 720 or 649.32 over 720. Doesn't make a huge amount of difference, and in reality these probabilities are way less than I've got here. Okay, the probability is like 10,000 or less to 1 at this sort of age. Around age late 30s, to 40, mortality is typically about 1 in 1,000 per year. So I've used extreme numbers to illustrate it, and when you've got mortality rates that low, the difference between the constant rate of death and the constant force of mortality is really completely immaterial. But you could get asked to do either. It's just simple. One is arithmetic, one is geometric, and it's all very simple really. Okay, so that's all you need to know about LX. There's more to it in terms of how we work out what the LXs are, but in terms of what it does with the how we calculate the TPX and the TQX, and then we can start and go on and look at actual annuities in the next lecture.